And if not, okay, so we should be recording. So let me do a brief version of the introduction once again. So welcome to Surajit Kalita, who is a postdoc in UCT MEM department working with Amanda Weltman, who received his Ph.D. in 2021 from the Indian Institute for Science in Bangalore. So very impressive CV and an expert in neutron stars, white dwarfs, and black holes. We're very glad you're here. Thank you for coming. And thank you very much for agreeing to talk to us this week, giving background on cosmology, and then next week in detail about your research. So may I ask, are you happy to take questions as we go along?
Yeah, sure. Yeah. You can stop me anytime. It's okay.
Ooh.
But,
Do you know him, man?
Oh my God, I know him. Yes, he's in badminton. I'm not joking.
Okay, so thank you very much for that testing of your mics. And I imagine Surajit probably won't be able to see hands raised, so I think just open up your mic and ask a question as we go along. And Surajit, please take it away.
yeah, sure. Let me share my screen. I hope it's visible.
Looks great.
Okay. So yeah, thanks, Will, for this nice introduction. And it's nice talking to some physics students, because although I'm in maths department, all my previous studies were in physics department. So it's nice to talking to you guys. So yeah, in this talk, I'll be giving a very brief introduction related to white dwarf, neutron star, and gravitational wave physics. And based on which most of my research have been done over the past 5 years, and which I'm talking about in my next talk. So in this talk, I'll be just some basic introductions of these things. And if you have any questions at any time, you can stop me and yeah, you can ask me. So this is a brief outline of my talk. So I'll be talking about very briefly about the stellar structures of basically white dwarfs and neutron stars. And then I'll be showing that how magnetic fields and rotations affect the structures of these white dwarfs and neutron stars, and why this magnetic fields and rotation is important, because then only you can actually generate some gravitational waves. And then I'll talk about some current observation status about these objects. But this I'll skip only 2-3 slides for this talk, but I'll be talking about more on this on the next talk, where I will be talking about some important physics that people have been researching over the first few years and some results. So let's start with the basic introduction of the white dwarfs. So what is a white dwarf? White dwarf is the end state of a stellar object of mass around. I'm coming for that. But let's start about our sun. Our sun is emitting its radiation through something called fusion reaction, where hydrogen fuse to becomes eventually helium. And in this reaction, basically, it emits some kind of photon, which we eventually see as the sunlight. So, the basic understanding is that it's happening for a long time, and it will still be continuing for many years. But what will happen? It has some budget. It has some number of hydrogens there. Eventually, it will be over. It will be decreasing. And what will happen if once all the hydrogens burning are over? And when it is over, then actually you will have left with lots of heliums. And that phase is called something called regent, where basically your core is kind of contracting, more of contracting, and outside is more of expanding because it has extra pressure now. And because of that reason, this phase is called regent phase. But eventually what will happen, because core is still contracting with high temperature, this helium will also fuse eventually to become beryllium, carbon, or oxygen. And this outside is no longer will be quite apart, and it will be just fallen apart, and it's called basically something called planetary nebula. And this core, inside core remains, and that core eventually stabilizes, and it's called a white dwarf phase. And to get a white dwarf phase, the initial star mass has to be of the order of our solar mass, star mass of the sun. A little bit higher is also fine. Exact numbers I'm coming in the next slide. But if let's assume the star is much more massive, in that case, this burning is quite faster. And what happens, because it has more mass, it has more gravity, it will no longer like this detachment of this outer layer to inner layer happens, and all of them suddenly falls here, and eventually it becomes a kind of a supernova. And when this supernova happens, only the core remains. But because here the fusion is quite high, because fusion is continuing because of high density, it's no longer stops at say carbon or oxygen. It might go all the way up to iron. And when it goes to that kind of phase, we generally call that a neutron star phase, which are very compact in size. However, if the star mass is much more higher than this, much higher, in that case, all this phase occur, but eventually this collapse is much more compared to these phases, and it's such high that it even enters a phase called black hole, where basically this inside matter goes inside of something called event horizon, something from where basically light still cannot escape. So it's become such a dense object, and that is basically called black hole. So whether white dwarf, neutron star, or black hole, it all depends on the initial mass of the star. And but in my talk, I'll be mostly focusing on white dwarf and neutron stars. I'll not be talking about black holes in this talk. So when I said about average star or massive star, what is the mass? Okay, look, before that, let me tell about the sizes of these objects. For example, white dwarfs. White dwarfs have generally size of the has a size of the Earth. So so it's like this is a white dwarf, which is basically Sirius B. It's the nearest white dwarf from Earth. You can see its size is very much comparable to the size of the Earth. It can be a little bit higher and lower than the size of the Earth, but it's approximately of the order of the size of the Earth. However, for neutron stars, it's much more compact, as you can understand, and its size is just diameter of around 20 kilometers, or radius is about 10 kilometers in size. But you can understand, see, the masses are almost similar. They are of the mass of the sun, but you can understand that sun is very big in size. However, their size is quite small, so their density is quite high. White dwarf density is high, neutron stars is much even higher. And as I have said about black hole, if it contracts more and more, it becomes something called event horizon, and matter falls inside this, and even you cannot see this because even light cannot come out of this. And this is a very famous image of event horizon telescope that people have synthesized. And here, basically, these are something outside matter that has been emitted, and by inside you can see it's a black. That means nothing, no ray, no light is emitting from there, and we cannot see that. That's why we see it's black. So these are the size comparison of these objects, these compact objects. Now, what is the masses of these objects? So white dwarf has a mass of the order of mass of the sun. Similarly, for neutron stars, I'm coming for black hole in a moment. But as I said, that if you remember, these are called average star, our main sequence star. You can understand that initial mass of the star has to be less than around 10 solar mass or so to become it a white dwarf. If it's in the middle, these are rough numbers, okay? Don't consider it very exactly that this and boundaries are quite strict. It's about 10 to 20 solar mass. It eventually fate is a neutron star. I mean, it's much higher, then it will eventually become a black hole. As I said, radius of the white dwarf is the size of the Earth, so it's roughly always less than 1,000 kilometers in size, whereas neutron stars are of the order of 10 kilometers in radius. And central density of the white dwarf is roughly of the order of 10 to the 10 gram per cc, or less than that. But for neutron star, it's much higher, 10 to the 14 to 10 to the 15 gram per centimeter cube. And similarly, surface temperature of the white dwarf is quite high, and for neutron star, it's much even higher. Now for black hole, there are two types of black hole. One is called stellar mass black hole, one is called supermassive black hole. Stellar mass black holes are those whose masses are of the order of, in this range, And you can understand that these black holes can be formed from the final state of an evolutionary sequence of a star, like I showed. That means a star dies after it burns all its hydrogen, helium, all this space, and it becomes a black hole. But for a supermassive black hole, the scenario is completely different because the masses are quite high, like million to billion stellar masses. And in that case, basically, it cannot be formed by this evolutionary sequence of a main sequence star. Because to be such a big white dwarf, big black hole, your initial mass of the star has to be also million to billion solar masses. So that's we do not see. So this evolutionary sequence is ruled out to give basically this supermassive black hole. But there are some other physics people have proposed, for example, primordial black holes and some others, which has been formed maybe at early universe. And so there are different scenarios to obtain this. And that's why these are called supermassive black hole and these are called stellar mass black hole. And importantly, supermassive black holes resides mostly at the center of every galaxy. Whereas stellar mass black hole can be anywhere in the galaxy, and it can be much higher in number than the supermassive black holes. And as I said, they have something called radius, which is called event horizon radius. This is for a non-rotating black hole. These are basically, you can, this is the radius below which you cannot see anything of inside a black hole. So that's why this is called event horizon radius. And these are the radius of the normal stars, I mean, compact objects like white dwarfs and neutron stars. Now, there is another important figures generally astrophysics people draw, which is called Hertzsprung-Russell diagram, which is basically called HR diagram in short. So here in this axis, generally it's plotted with temperature for easier purpose. And in this axis, y-axis, we generally plot the luminosity. And you can understand, see, it's very important that the temperature increases from right to left. So it's slightly opposite in convention. But this is where all the main, our normal star rise. For example, our sun lies roughly here, which says luminosity here. And this is basically where our sun lies. And if you remember, these are the other phases like red giant or supergiant, all these phases. And those basically lie in these areas, basically giants and supergiants. They have different evolutionary path here. But this is called main sequence, and these are giants and supergiants. And this is white dwarf phase, basically, where you can understand white dwarf's temperature is higher than our normal star, but its luminosity is much lower than the conventional star. So you can see it's around 2-3 order of magnitude lower than this, main sequence star. For neutron star, it should be much lower because, but to detect a neutron star, it's not quite easy. And so people, I don't see people generally plot neutron stars in HR diagram, but its luminosity should be much lower here. So this is a brief idea how you can put all the stars in just one figure, whether it's a compact star or a main sequence star or in between phases. So now, as we can understand, now I'll be talking about only about white dwarfs and neutron stars. I'm no longer speaking about this main sequence and giant and supergiant phase. And these white dwarfs are in equilibrium condition. So we have to understand its structure, that how basically the white dwarfs or neutron stars retain its structure. So to get that, I'm going to use a little bit of physics and a little bit of maths, very simple equations, but yeah, that would be easier to understand. So a white dwarf, suppose I'm considering a non-rotating white dwarf, and so then it's assuming it's spherically symmetric. You can understand if it's in equilibrium condition, it's in equilibrium, that means your outside pressure and inward pressure both should balance each other. If one is higher than that, suppose the outside, this red one is higher, then it will be collapsing. And if blue is higher, then it will be expanding. But we see white dwarfs in an equilibrium state. That means these two has to balance each other. Now, what is rate? How this rate pressure comes? Because this has matter, so it has gravity, and gravity acts inward. So this inward pressure is due to gravity, whereas outward pressure, because white dwarfs has some kind of electrons, so they exert some different pressure, and that pressure actually gives you this outward force, and these two forces actually balance each other. Now, what is the inside force? It's gravity, and you can understand from simple Newton's law, this is the force due to gravity, whereas what is the force due to this gas? It's just area multiplied by the pressure. For example, let's take a small cut from here. It would look like a cylinder. You can understand the radius is of the order of dr, say of dr, small radius, and its area is roughly a. Then force of gravity acting inward, and the outside pressure, outside force is just a into dp. So these two balance each other. Similarly, for mass, we know this is what is the mass of an annulus. You can just get it like the density multiplied by the small infinitesimal volume. So these two equations are very important. And if you just substitute dm here and a little bit calculation here and there, you can find out that we can get basically two equations. One is called dp-dr equation, and another is dm-dr equations. And the first equation is called pressure balance equation, and the second equation is called mass estimate equation. So these two equations are very important that I'll be talking about even in the next, in a few slides later. Now, I have these two equations. Now, you see, I have how many variables? I have P, M, and rho. I have three variables. R is just independent variable. But I have three dependent variables, but I have just two equations. That means these two equations cannot be solved exactly. So I need one more equation. Let's try to figure out what's that equation. And to get that equation, we have to basically that equation, if I give you a hint, beforehand, that equation, we are going to derive a relation between the pressure and the density. And what does pressure and density relation means? What is the matter inside? What kind of matter is there? That basically governs the relation between pressure and density. And because here mostly white dwarfs has electrons, they follow the famous Fermi-Dirac distribution because those are fermions. But in a white dwarf, it's important that its Fermi energy is much, much higher than its kinetic energy or thermal energy. So in that case, this complicated looking Fermi-Dirac distribution can easily be written in this approximation, which is basically a step function. That means if energy is less than Fermi energy, this function goes 1, otherwise it's 0. And if you know little studied statistical mechanics, you know this condition can also be obtained if you just simply put t equal to 0 here. So that means this calculation, the white dwarf matter, we generally call said it's cold matter. So white dwarfs are assumed to be cold. Although, as you can understand in a few slides back, white dwarf has very high temperature. It's higher than our sun temperature, temperature of our sun. But because its temperature is less than Fermi temperature, white dwarfs are assumed to be cold. And that's why this zero temperature calculation is a very good approximation for white dwarf matter. So once you understand this Fermi-Dirac distribution, you can simply write the number density and the pressure from these simple relations. And you can understand generally this integration has to go from 0 to infinity, but because we are restricting with just 1 and 0 function, and this integration is valid, I mean, non-zero when this is less than EF. So, or in terms of momentum, we just wrote it in P. So it goes from 0 to PF. So these are the two equations, and number density and matter density are related. Okay, I forgot to write that expression, but it's just proportional. Matter density is proportional to number density. That means rho and number density are proportional. Now, if you calculate this integration, let's take two different limits. One is non-relativistic and another is relativistic limit. you can simply write in non-relativistic limit, this is dominating, whereas relativistic limit, this kinetic term is dominating. So accordingly, you can write the relations, these two relations can simply be written as in terms of P proportional to rho per 5/3 or P proportional to rho per 4/3. And this is called non-relativistic equation of state, and this is called relativistic equation of state. So you can understand equation of state means relation between pressure and density. But sometimes people generally just say 5/3 equation of state or 4/3 equation of state. That's a common way of saying it. It simply means P is proportional to rho power that factor. But these are some approximation. One can actually solve this integration exactly, and which Chandrasekhar did in 1935, and he obtained this famous equation. And this, you can also take the limit here, like x much less than 1 or x much higher than 1, and you can do some Taylor series expansion, and you will get also this same approximations. So as you understand, I already had these two equations, as I said, but I required one more equation, and that equation is now my equation of state, relation between pressure and density. So now I have three equations, three variables, they are exactly solvable. But because these are differential equations, I have to put some boundary conditions. And these are some simple boundary conditions, like at the center, mass has to 0, and towards the surface, when I reach the surface, mass will be the mass of the star, mass of the white dwarf. Similarly, for density, at the center, density is maximum. And when it's, as I'm going out gradually towards the surface, it will be mathematically, it falls to 0 when it reaches the surface. And or the pressure, because pressure and density are proportional, so you can use either these two conditions or these two conditions, they are the same. So now you have all three conditions, you have boundary conditions. So you solve these equations exactly with the value of some particular rho c, with some particular central density. For example, let's consider a central density of 10⁻⁷ gram per cc. I'll be using some simple differential equation solver method to solve these two equations with this rho c fixed now. And as I go out and out, my density decreases, and when it goes to 0, that's my surface. And because I'm solving both the equations simultaneously, my mass is increasing from 0 up to some value. And you can see when it reaches the surface, the mass turns out to be around 0.8 solar mass. And the radius is about 7,000 kilometers. That means for a 10⁷ gram per cc central density white dwarf, the mass and the radius are fixed. But similarly, if I change the central density, now suppose rather starting at 10⁷, I start with 10⁸ or 10⁶, then also my mass and radius are changing. And once you do it for all the possible central densities, you will get different masses and different radius. And once you plot all of them together, we get the famous Chandrasekhar mass radius curve for white dwarfs. And here, basically, each point of this curve, this solid curve, represents one white dwarf, basically, which basically has different central densities. And you can understand, you can see, for example, at this low density limit, this dotted line fits with this line. This is because at this case, it's non-relativistic assumption, this rho per 5/3 assumption is valid. So this is basically, if you just consider rho per 5/3, so this is valid, and this dotted curve is for rho per 4/3 equation of state. But yeah, let's focus only on the exact equation of state, exact mass radius curve. And you can see after some mass, even if you increase central density, your mass do not increase. And this particular phase, this particular mass is called Chandrasekhar mass limit, which is very famous because he got Nobel Prize for this. That means a white dwarf maximum possible, a non-rotating white dwarf can have maximum possible mass of around 1.44 solar mass. And it no longer increases even if you increase the central density. And important factor, thing for the Chandrasekhar mass is that this is the exact expression. You can see H is the Planck constant, C is the speed of light, J is gravitational constant, MP is the mass of proton. So all are fundamental constant. And this only factor which is not fundamental, it's basically mean molecular weight of the element, for example, white dwarf is made of say, carbon, then mean molecular weight means your atomic mass divided by atomic number. So for carbon, atomic mass is 12, atomic number is 6, so 12 by 6 is 2. So this Chandrasekhar mass limit just simply depends what's the matter inside, and it's not dependent any other factor because all others are constant. So this is about the mass radius curve. But if you remember, all these equations, this pressure balance equation was non-relativistic. Oh, sorry, these are Newtonian. But suppose I use some general relativistic effect eventually here, how it changes. So if you remember, these two equations were Newtonian equations. If I put general relativity, I didn't show the derivation here, but it's quite straightforward if you know the Einstein equation. You can show actually this pressure balance equation simply modifies little bit complicated form, but mass balance equation do not change at all. So now I have two equations, dpdr and dmdr as earlier, but dpdr is now modified. And I have the same boundary conditions and same equation of state. In that case, let's solve these two equations again, and let's see what we get. And you can see, already I have shown this red dotted line, and this basically this is the same line which Chandrasekhar got. And this GR calculation gives you roughly similar mass radius curve, except at the high density, when the density is quite high. And at these densities only, it starts to deviate. But at low density, they are matching pretty well. That's why mostly astronomers still use Newtonian cases, just because it gives very nice result. But there is a very important factor, important difference here. What does Newtonian calculation say? That your limiting mass, that means that 1.44 solar mass, is obtained only when you get identically or mathematically you get zero radius or infinitely high density. So your curve will go down and density will go up. So that's basically the mathematical condition, but we know that that is not possible physically because zero radius object with infinite mass is quite, imaginary. But what does general relativity says? You can see the curve increases here, and then after this point, this curve turns back. That means even after increasing density, mass starts decreasing. Now, as you remember, these equations are called equilibrium equation, hydrostatic equilibrium. So these stars are in equilibrium, but whether they are in stable equilibrium or in unstable equilibrium, simply from here, we cannot say. So you have to do something called stability analysis. And generally you take a star, you part of the star and see whether the star oscillations in a star grows or decays. And thereby we say whether the stars are stable or unstable. You can show basically all the stars in this branch up to this maximum point are stable. But once it turns back, these stars are unstable. That means those stars should not be observed in nature because those are unstable stars. Some different effect is happening everywhere in the universe. So that star, even if it exists, it would have been blown up by now. So this is the maximum possible mass according to general relativity. So its value is something similar, roughly 1.4. Value-wise, it doesn't differ too much with the Newtonian. But physically, it's pretty different because according to Newton, as I said, you get the maximum mass only when you get zero radius or infinite density. But GR says you get that maximum mass at even finite radius and finite density, which is quite physical compared to Newtonian. So GR wins in that sense from Newton. Now, suppose, as I said, these are the maximum masses of the white dwarf. Now, suppose I have a white dwarf here and I have a main sequence star, that means some low gravity star. White dwarf has high gravity, so it will start accumulating matter. But we know, and once it starts accumulating matter, its mass will increase. But we know that its mass should not increase than this mass limit, Chandrasekhar mass limit. So what will happen if it gets more mass than that? Then basically this pressure balance no longer sustains, and this white dwarf bursts, and it bursts out to produce one type of supernova, which is called type 1a supernova. And these supernovae are very important because you can understand they burst at somewhat around similar mass, at Chandrasekhar mass. They have very similar in peak luminosity, and their declining curves are also very. I mean, you know what is the declining curve, and because of all this fixed stuff, people generally use type 1a supernova as one of the standard candles to measure distances in cosmology. So in that sense, type 1a supernova is very important. And how do you know whether it's a type 1a supernova? If you take the spectra of any supernova, and if you see it doesn't have any hydrogen line, but if you see a silicon absorption line, for example, here, these are silicon absorption line at around 6,000 angstrom. So you say those supernovae are called type 1a supernova. So I'm just skipping here, because if you want to know more about type 1a supernova, I can talk to you separately later. Now, whatever I've said about these things are about white dwarfs. So what about neutron stars? So for neutron stars, these two equations are still valid because they are hydrostatic balance equations. However, in neutron stars, what's the matter inside? Like in white dwarf, we know those are degenerate electrons, like I showed earlier. But in neutron stars, we don't know what's the matter inside. It's because neutron stars have very high density, and that high density, exactly what is there, nobody knows. So people have proposed different matter constitution, different reactions, different high energies, and so thereby you get different relation between the pressure and density. That means you get different equation of states. Now, once your pressure and density are different, even though your dPdr and dmdr equations are same, you get different mass radius relations. And you can see these are the different mass radius relations people have proposed. There are much more than this. So which equation of state is correct, or which mass radius relation is correct? It's not known. That's the biggest problem. But people have proposed some kind of bound so far, like this current bound is 2 solar mass. That means any mass radius curve which gives you maximum mass less than 2 solar mass are ruled out. That means suppose I have a curve which goes like this, and it just turns here. That means its maximum mass is no longer 2 solar mass. So that equation of state is ruled out. And why this 2 solar mass? Because people have observed some pulsars, which are basically neutron stars, rotating neutron stars, so which have mass of around 2 solar mass. Even current gravitational wave detection, people have proposed slightly higher than 2.1 solar mass. Then even, say for example, this pink and blue curve will also be ruled out. So these are different. I mean, from observations only, you can put some constraint on this equation of state, but we still don't know among, say, for example, which one is correct among these equation of state. So that's just one slide of neutron star, because I'm just wanted to talk about the structures. Now let's see what's the effect of rotations and neutron magnetic fields on white dwarfs and neutron stars. As you know, these two equations were valid when they had no magnetic field and no rotations, the star objects. Suppose you have rotation in the system, basically the white dwarf or neutron star is rotating, and people have shown that rotation can increase the mass of the white dwarf or neutron star. So back in 1968 itself, Ostraker and Hertzsprung showed that mass of the white dwarf can increase up to 1.8 solar mass. So you can understand, as we have said earlier, about 1.4 solar mass is the maximum possible mass. That's basically a non-rotating white dwarf. That's Chandrasekhar mass limit, but that can increase in the presence of rotation. Similarly, this group, German group, they have shown that mass of a neutron star can also increase like 1.2 times its original value. Like if non-rotating neutron star has 2 solar mass, then rotating neutron star can have 2.4 solar mass also. So not only it increases mass of the compact object, but rotation also changes the shape of the object because of the centrifugal force. That means, suppose this is a white dwarf or a neutron star. This white dwarf is an example. Suppose it's rotating, and because of centrifugal force, you can understand its equatorial radius increases, but polar radius it doesn't change much. But this is basically distorts the shape. And because of this distortion, it has more volume now and it can accumulate actually more mass. So thereby, basically, rotation can change the shape as well as increase the mass of the compact object. What about magnetic fields? For magnetic field, it depends on the magnetic field structure. For example, I am considering two different magnetic field configuration. One is called toroidal and one is called poloidal. So poloidal fields are quite obvious. You will know, like there is an object and field lines goes like this. It just goes from North Pole and enters from South Pole and so on. Toroidal fields are like torus-like structure. You can understand like donuts. So these field lines have like donut-like structure. And you can understand, suppose I have this poloidal field, magnetic field gives extra pressure. And when magnetic field exerts extra pressure, because the field lines are in this direction, the extra pressure will be in this particle direction. As a result, it changes the object in this shape. However, for toroidal field, the extra pressure is from equatorial direction. So extra pressure will be from equator, and it changes the object of spherical object to an oblate shape. Prolate shape. This is an oblate and this is a prolate. And if you remember, rotation also makes it an oblate. Now, suppose in a white dwarf or neutron star, you have both magnetic field and rotation, which is the case for most of the, almost all of the white dwarf and neutron stars. So eventually its shape will be a prolate shape or an oblate shape, depends on whether your magnetic field is higher or rotation is higher. As a comparison, you can put some magnetic field energy and rotation energy, and you can show which one is higher. Accordingly, its shape will be a prolate shape or an oblate shape object. And from here, you can also understand, suppose a non-magnetized white dwarf has say 1.4 solar mass, which is the Chandrasekhar limit. Now, in the presence of magnetic field, whether be it a poloidal field or toroidal field, doesn't matter, its mass always increases. So to summarize, your magnetic field can increase the mass and also rotation. So magnetic field and rotation both can increase the mass and mass of the compact object, as well as it can deform the shape of the compact object. And those will be very important when I'll be talking about gravitational wave, but on not this talk, but on the next talk. So I'll be using these structures again in my next talk. Now, when I'm coming to gravitational waves, let's go in a very few slides about gravitational waves. I'm not going to show much equations here. So what kind of system exerts emits gravitational waves? The idea is that there's a thumb rule that any system, any object which has a non-zero time-varying quadrupolar moment, that object can emit gravitational waves. That's the only requirement to emit gravitational waves. And probably I've heard that LIGO, Virgo, even recently Kagra has detected many gravitational waves from the merger objects. I'm coming in a moment to that. And many interesting objects, for example, intermediate mass black holes. As you remember in my earlier slides, I have talked about stellar mass black hole and supermassive black hole, but there are some black holes which are called intermediate mass black hole, which mass falls between the range of stellar mass and the supermassive black hole, for example, this one. So such objects have, for the first time, have been discovered by gravitational waves. Similarly, another object called this 2.7 solar mass, and people still don't know whether it's a high mass neutron star or a very low mass black hole. So those are also in debate. But yeah, those are very interesting objects people have observed so far with these gravitational wave detections. And yeah, LIGO Virgo are still being upgraded with different machineries. And around 2035, a space-based mission named LISA is proposed to launch, maybe a little bit after this year. So what is the effect of gravitational waves? Suppose your gravitational waves is falling on the plane of the screen, and suppose you have a ring of particles. Now gravitational wave has a phase difference of 45 degrees. It's something similar you can understand about electromagnetic waves. For electromagnetic waves, you have two polarization modes. One is electric field and one is magnetic field, but they have a phase difference of 90 degrees. Here also for gravitational waves has two polarization modes if you consider general relativity. But those have a phase difference not 90 degrees, but has 45-degree phase difference. That means when the gravitational waves falls, as time passes, if it changes the shape of the object to like this in time, that means in this direction, this is called plus mode, then the cross mode will be changing the shape of this bunch of particle in a 45-degree compared to this direction of the plus mode. So these are the effect between the two modes of polarization of the gravitational waves. Now, as I said about LIGO and LISA, so if you remember, if probably you know that LIGOs are basically, there are some detectors in US. So they are basically like interferometer, like Michelson interferometer, somewhat similar. So you put some kind of laser here, and when the gravitational wave pass between these two arms, basically, suppose your say plus mode is falling. I'm just giving an example, and you have laser among the here and here in perpendicular direction. Then once the laser on one side will be squeezed, and the laser will be other side will be slightly elongated, and that deformation can be people have measured, and thereby they have confirmed those are gravitational waves. And in the space-based mission, LISA, that I have spoken, they will not have like two arms, rather it would have three arms, basically three detectors will be here, and they will all be running simultaneously, but that's a proposed mission for the future. So how gravitational waves have been detected? For example, from the merger events, that so far whatever gravitational waves have been detected, those are from merger events. That means you have two objects, say for example, two neutron stars, they are rotating around each other. They are emitting gravitational waves continuously. And once they are emitting gravitational waves, they are coming closer and closer. And after a certain time, they merge. And when they merge, they emit quite a significant amount of gravitational waves. Its amplitude goes pretty high. And after that, there is something called ring down. It becomes a single object after that. And when it becomes just an isolated object, its gravitational waves is almost like, just zero roughly. And this phase is called continuous gravitational waves that I'll be talking about in my next talk again. And you can understand why current detectors can only detect the merger events. You can understand because at the time of merger, the amplitude of the gravitational waves is quite high compared to the in-spiral phase. But in the future, people are still doing some upgradations of LIGO Virgo detectors. So in the future, even this continuous wave can also be detected. And then it will be a more better science we would be able to know. So what kind of objects this gravitational wave detector have detected so far? It has detected like a merger of two black holes. For example, this is a black hole, this is a black hole, and the final product is a black hole. Similarly, merger of two neutron stars, for example, this is a neutron star, this is a neutron star. Merger is what we don't know whether it's a neutron star or black hole. There is confusion on this thing. So these are basically different merger events people have so far observed, and this is in short called stellar gravity. X-axis is nothing, just y-axis is important. The masses, basically which two masses are combined to become one single object. And so far, these are the different gravitational wave detectors around the world. These LIGO detectors are in US, these are in Europe. Kagra has been started running in Japan, and LIGO India is proposed to run, say, in 3-4 years. And once all these detectors will be running, it will be much better because you can then localize the source much better. Right now, we don't know the source location exactly. You generally give a path, but once all the detectors are running, you would be able to better localize those objects basically. And what kind of objects we can detect? For example, these are called sensitivity curves of gravitational wave detectors. For example, this is a sensitivity curves of LIGO, and anything that falls above the sensitivity curves are detectable. If it falls below, it cannot be detected. For example, you can see compact binary in spirals. That means two objects are rotating. still it's not able to detect by LIGO because it's false below LIGO sensitivity range. But once say advanced LIGO will be, or Einstein telescope will be completed, then you can see they are also will be able to detect it. Similarly, for LISA, it will be able to detect lots of binaries, galactic binaries, white dwarf binaries, and some other objects. And you can understand these are the frequency range. So current LIGO detectors can detect gravitational waves more than 1 hertz of frequency. But LISA will be able to detect gravitational waves frequency which will have less than 1 hertz of frequency. And similarly, some pulsar timing array, which are already being running in different groups in the world. So they will be able to detect some kind of stochastic background and so on. So this is a very rough picture, like what kind of objects are there and what kind of objects can detect, which telescopes can detect what kind of objects. And these are basically these are some running detectors, but all others are basically futuristic proposed detectors. So this is all about the basics of white dwarf, neutron stars, and gravitational waves. So in the next couple of slides, I'm just giving some hint of what I'm going to talk about in my next talk. Just in 2 slides, I'll be talking about. One very important property, as you remember, as I said, like if a white dwarf bursts, it will become a type 1a supernova, and type 1a supernova have roughly fixed luminosity. But recently, like this Nature paper in 2006, they have observed something called overluminous type 1a supernova. That means supernovae, those have much higher in luminosity. And how to explain this phenomena? One object is that they burst at much higher than the Chandrasekhar limit. For example, for this kind of burst, you need this kind of white dwarf masses. And you can understand to get these masses of the white dwarf, we need to incorporate so non-rotating white dwarfs cannot have this mass. And that's why I have talking about rotation and magnetic fields. So they can increase the mass of the compact object, and they can actually explain this kind of phenomenon. Similarly, there are not only rotation and magnetic fields. People have proposed hundreds of different mechanisms. For example, you modified the theory of general relativity, or you introduce something called non-commutative geometry, some quantum gravity effect, basically. And then also you can explain such overluminous type 1a supernova. But the problem is, which theory is correct? We don't know, because we do not see those white dwarfs directly. We just know its mass from the luminosity observation of the type 1a supernova. So how to know which theory is correct or which of them to rule out? Then gravitational wave will be a very important factor that I'm going to show next talk. That's why I have shown that much introduction of gravitational waves. Similarly, something called fast radio bursts, which have been started working here at UCT. So those are also something very bright radio transient events. That means they have observed by radio telescopes. They are very bright and they observe for a very fraction of a second. They are quite instantaneous. And so far, like 700 or so have been detected. But the problem is some of them are repeaters, some of them are non-repeater. That means some FRBs have been observed repeating after some time, and some have just observed once and never observed. So then also people have proposed like more than 50 theories to explain FRBs. So which theory is correct? Again, we don't know, because current observation cannot say. But as I have, I'll show that gravitational observation can also give you some restriction in terms of which theories can be ruled out or which theories would be more probable. Similarly, some other objects called soft gamma repeaters and anomalous X-ray pulsars, these are also basically observe some burst, basically, some pulsars, and they observed in X-rays and gamma rays. And we generally find for most of them has some supernova remnant to associate with them. And once you know those have some supernova remnants, you can actually conclude that those are neutron stars candidate. But for some, this SZ and XPs, people have neither observed any supernova remnant nor any direct magnetic field have been done or any direct observation. So people have proposed that they can be white dwarfs also. So again, there is a dichotomy here, like whether they are neutron stars or white dwarfs, we don't know. And here also gravitational waves can play an important role to distinguish whether they are neutron stars or white dwarfs. Similarly, there are another objects which are called white dwarf pulsars, and their masses are also not known. People have given, with the current observation, a range of mass limit. And in that sense, that's also still unknown. So these are the 4 objects, 4 topics. Basically, super Chandrasekhar white dwarfs have not been observed directly. Progenitor theories of FRBs are not known, and exact nature of some FRB, SGRs and EXPs are not known, and masses of some white dwarf pulsars are not known. And how to know how to address all these issues, just you need gravitational waves, and through gravitational wave observation, you can put very nicely some limit on these things. And yeah, that's basically my next talk. And these are my collaborators, like Amanda is a professor, and others are some student collaborators, like master students, and some are faculties, and so. And yeah, our group generally has lots of student projects. So if someone is interested, they can either contact Amanda or me directly, then we can think of some nice projects doing together. So yeah, thank you.
Super. That was very, very good. Do we have questions from the audience?
Hi, yes, I have a question. At the beginning, when you did your derivation for the mass, and you used your force of gravity and as on the external, and your force of pressure from the internal, and then you got your 2 equations, and then you used electron gas to model or to obtain your density, if I understood correctly. Why, in the case of your star, why is it okay to only make use of an electron gas? Because surely your star also contains a lot of nuclei that actually won't have the most mass of your star as well.
Yeah. See, yes, of course. So the idea is, whenever I talk about the mass of any object, that mass is coming mostly from the nucleus, because electrons generally don't have any mass. So whenever I say carbon white dwarfs, that means its masses are coming from the carbons. But for pressures, it's quite different, because now the electrons no longer are bound states of the nuclei. They are come out, and those are called basically degenerate electrons. And they basically movable, more momentum. And because of that momentum, they can exert actually more pressure than the nucleus. And that's why the pressure is mostly due to the electrons and not due to the nucleus.
Okay, I see. That makes sense. Thank you. Don't you also, I might have seen incorrectly, but don't you also use your density to plug into your, so do you essentially only use the density for your expression of the pressure, and not also, because you also took the internal gravitational force into account for your expressions? So will the density essentially only play an effect on the pressure and not on that force due to the mass as well?
Yeah, because you can understand these are basically something like macroscopic properties. You can understand these hydrostatic balance equations. Those are macroscopic. That means your pressure or balances are due to some big matter. Whereas this equation of state, it's a microscopic quantity. I mean, microscopic in the sense it's due to what is there inside. What's happening at quantum level. So in that case, whatever is coming, the pressure is only dependent on the density. It's microscopic scale, and gravity doesn't play any important role in that scale. I mean, any significant role compared to this thing. And that's why we do not incorporate effect of gravity in this equation of state. But yeah, there are different research people have done. But yeah, eventually you can show those effects are quite negligible.
Okay, that makes sense. Thank you.
Like,
Super, very nice. Maybe I could then just follow up before there are other questions. So you have this electron degeneracy pressure, and if that is not to overcome the end of life of this object as a white dwarf, then if the electron degeneracy pressure is overcome, do I understand correctly? That's when you have a supernova, and then you can either have a neutron star where there's a neutron degeneracy pressure that is not overcome by gravity. But if that is overcome by gravity, then you get a black hole, yes?
Yes, yeah. But then you don't have basically intermediate the white dwarf phase, because it's the star, like in white dwarf, the star starts collapsing, stop collapsing when the radius say around 1,000 kilometers. But if your mass is more, it doesn't stop there. It will still collapsing. So the 1,000 kilometer gone easily, and it just resides say at 10 kilometers. So.
I'm sorry,
Hello.
I have yes, the power just came back on. So I think that there was a bit of a hiccup with the internet. I guess the thing that is surprising to me is that it's not like there's an additional explosion when the neutron pressure is overcome. The supernova only comes from the when the electron pressure is overcome.
No. There are two different observations. Basically, one is called type 1a supernova that I have showed. This one is due to white dwarf. That means a white dwarf is there, something is happening, and it overcomes, and then it happens. But for neutron stars, it's the opposite. If you can understand. So for type 1a supernova, it happens after white dwarf phase. But for neutron star, the supernova, like 1b or type 2, say all this supernova, happens before the neutron star is formed. So it happens after this red giant stage, this planetary nebula, these masses can no longer go back because of high density, and it falls very fast, and it becomes a type 1 supernova, type 2, or I mean core collapse supernova. And then the core remains because of the high density, the fusion goes up to iron, and then it becomes more of a neutron star.
Is there any kind of binary system where a neutron star continues to accrete mass from another object and then the neutron star collapses to a black hole?
Yes. The recent example of gravitational waves, say GW170817, when two neutron stars merges, finally collapse, and it finally becomes a black hole of around 2.7 solar mass.
I imagine that must be a very violent event.
Yes, of course, but and that's why that's the most important gravitational wave observation so far, because that event is not only been observed through gravitational waves, but its electromagnetic counterpart because of magnetic fields, and so it emits some EM radiation, and it's been detected by X-ray to gamma ray to radio telescopes. So every detector could detect that particular event. So that's basically, yeah.
That's excellent. Very good. Are there further questions from the audience? Okay, well, if not, then let's thank the speaker one more time.
Yeah, thanks. I hope it's understandable.
I thought that was fantastic. I really appreciate it. And we look forward to hearing from you next week. It may be in person, it may be, again, virtual, but either way, we are very much looking forward to it. So thank you very much for an excellent talk.
Yeah, sure. Thanks, pleasure. And yeah, thanks everyone for attending. Yeah.
Yeah, thank you.
Very nice.
Yeah, thank you. I hope to see you in person next week.
Oh, yes, definitely.
Yeah. So if anyone has any doubt or anything, you can also come to me or write to me. That's fine.
Super. Thank you. Okay, take care, everybody, and goodbye.
Bye-bye.
Thank you. Goodbye.
Bye.